Hello students and welcome back to my channel. In this video, I have come up with the photoelectric effect topic. Okay, probably I'll be doing this in two videos, uh, which will be very helpful for class 12 board exams, and at the same time they'll be equally helpful for Neet as well as JEE mains also. Most of the students, they have a complaint that they have not understood photoelectric effect completely. There are minute, misconceptions here and there. So in this video, I would like to resolve all your queries and all your misconceptions gradually. Okay. So without wasting time, let us start the first half of this photoelectric effect. Now, basically, students, we have to understand what is electron emission, because in metals, electrons can be made to be emitted. Suppose this is a metal. Okay. We are studying electron emission. As we all know that metals have lot of free electrons. There are abundance of free electrons here and there. They keep moving within the interatomic space. Even though, so to say that they are free, but they are not so free so as to come out of the surface. Okay. If we want them to come out of the surface, then we should supply certain energy to them, because as soon as an electron tends to come to the surface and move out, the rest of the part becomes positively charged, because loss of electron is equivalent to a positive charge, and this positive charge will immediately attract the electron towards the inside of the metal. So that's why even though free electrons keep moving here and there, but they are not able to come out of the surface. So our intention is to make them come out of the surface. So naturally, we have to supply that necessary energy through which they will be able to overcome these attractive forces of positive ions inside, and then they'll be able to come out. Right, students? Now, that means it is very clear that there has to be a certain minimum energy required by the electrons. Okay, in order to come out. That is known as work function of the metal. Very important term, students. Work function of the metal. So it is the minimum energy required by an electron to come out of the surface. Okay, students. Now this will be expressed in electron volt normally, because electron itself is a very small entity. So needless to say that we cannot use joule or erg. Joule or erg will be too large a unit to be expressing the energy of electron. So the more suitable unit is electron volt. So as you might be knowing, students, in electrostatics we have studied that 1 electron volt is the energy acquired by the electron when accelerated through a potential difference of 1 volt. So as we know that electron carries negative charge, so they will be accelerated opposite to the field. They will be accelerated opposite to the field. So the energy acquired by an electron when accelerated through a potential difference of 1 volt is actually 1 electron volt. And this energy is acquired by the work done due to the electric field. The electric field does work on the charged particle during acceleration. Okay, students? One more thing here itself I would like to say, that if a charged particle has any charge, and if it is accelerated through, let us say, I take it as m volt, then the energy acquired will be n m electron volt. Okay, n m electron volt. This formula has come directly from the formula which we have already studied, that the work done by electric field on a charge is charge multiplied by potential difference. This is the work done by an electric field when the charge is accelerated to a potential difference. Okay, students? So with that, we have come across this formula. Second thing you have to understand, that suppose an electron with the initial kinetic energy K, let us say K naught, okay, is made to retard by navigating, let us say, potential difference delta V, so that its final kinetic energy becomes 0 exactly. Then work done against the electric field by the electron will be Q delta V. So here it will be what? The work done will be equal to its own kinetic energy, because it does work at the expense of its own kinetic energy. So the work done will be equal to E into delta V electron volt. Okay, students? Sorry, E will not be there because E is 1. So we have delta V electron volt because E is 1. Okay. So on this aspect, we can call this as the stopping potential for the electron. Stopping potential, okay, for the electron, because this potential could exactly stop the electron. This potential could exactly stop the electron. That's why we call this delta V as the stopping potential. The potential which exactly stops an electron. Okay, right. So this one is clear about, students. Now we are discussing basically electron emission. So for an electron to come out of a metal, it will require certain energy which is equal to the work function. So we have to supply that work function. So on that basis, we can divide all the types of emission into three categories. Okay, students. So three types of electron emission are possible. One is thermionic emission. Thermionic emission. Then the other is field emission. Field emission. And the last one, which we will discuss in detail, is the photoelectric emission, or simply we can call it as photo emission. Photo emission. Okay, students. Right. Now, thermionic emission, as the name itself implies, that the metal wire has to be heated. So when a metal wire is heated, okay, then basically we are supplying the heat energy. So these electrons, the free electrons, they absorb this heat, and if they absorb an energy greater than or equal to work function, they'll be able to overcome the attractive forces and they'll be able to come out. So this type of phenomena in which the electrons are ejected when the metal wire is heated to an appropriate temperature is known as thermionic emission. In olden days, all the electronic equipments, okay, used to work on diode valves and triode valves, particularly the radio and televisions and tape recorders also. So we used to have diode valves and triode valves. So they used to work on thermionic emission. Okay, now it is outdated. Now it is no longer in use. Next is field emission. Now suppose you have a metal, students, and it is subjected to a strong electric field. Okay, as you know, as soon as the free electrons are subjected to electric field, they'll experience a force. Yes or no? If the electric field is strong enough, maybe of the order of 10 to the power 8 volt per meter, then it's possible that the electron will be so strongly pulled that it will permanently be pulled away from the atom, and not only atom, it will be able to come out as well. So this way of emitting electron by applying a strong electric field is termed as field emission. And finally comes the photo emission, which is the subject matter of our discussion. In this particular situation, we supply the necessary energy to the electrons by irradiating the surface with light of suitable wavelength. Why suitable wavelength? Because if wavelength is proper, only then the required energy will be able to, eject the electron, the energy supplied by the photons. So this way in which the light is able to eject electrons is known as photoelectrons. The incident light is able to eject photoelectrons. If it is ultraviolet light, then it's quite easy to see. But if it is visible light, only certain metals will show this phenomena. For example, cesium will show photoelectric effect with violet light or blue light. Okay, so this is the subject matter of our discussion. I hope that is clear, students. Right. Now, why these electrons will be termed as photoelectrons? Photoelectrons, because these electrons are the result of incident light on the surface. So I hope that is clear, students. Then next we'll be seeing the photoelectric effect, which we have picked up the topic photoelectric effect. So it is the phenomena in which certain metals, when irradiated with light of suitable wavelength or frequency, eject electrons from the surface. Such metals are known as photosensitive metals or photosensitive substances. Not all show photoelectric effect. Photosensitive metal. Okay. Particularly the alkali one metals, they are highly photosensitive. Okay. Sodium, potassium, cesium and all. So this is what we are going to study. Okay, students. Then in this regard, we should understand one basic theory, which is Max Planck's theory. Max Planck's quantum hypothesis. Okay. According to this theory, when electromagnetic wave, particularly light, ultraviolet light or visible light, when it interacts with the matter, it always interacts in terms of discrete energy packets. Suppose this is a matter, anything, solid, liquid, gas. Now light is incident on it, is made incident on it. Then basically it will be in the form of discrete energy packets, which will be known as the quantum. In case of light, they are known as photons. So discrete means well separated from each other. Energy packets, discrete energy packets. In case of light, they'll be known as photons, or in general, they'll be known as quanta. Plural of quantum is quanta. Okay. We can treat them as particles. They can be treated as particles because they have momentum as well as energy. Okay. So momentum carried will be h by lambda. Momentum carried, and kinetic energy will be h c by lambda. Okay. I should not say kinetic energy. I should say energy, or h into nu, where nu is the frequency. They keep moving with a speed equal to that of light, that is 3 into 10 power 8 meters per second in vacuum. Okay. So for all practical purpose, we'll assume that when light interacts with matter, it interacts in the form of photons, and these photons can be treated as particles, material particles of momentum h by lambda and energy h nu. And one thing you have to remember, students, the photons owe their existence to their energy itself. If they lose their energy because of some collision or something, then the very existence of photons disappear. The photons will totally disappear, and there will be no trace of any photon. So photons owe their existence to their energy. If they have energy, that means they exist. If they don't have energy, means no photon at all. Okay. Now, while we apply this, while we treat this as a particle, law of conservation of energy and law of conservation of momentum can always be applied during the interaction of photons with matter particles. So during interaction of light with matter, the following can be applied. The following can be applied. The first is law of conservation of momentum. Law of conservation of momentum. The second is law of conservation of energy. Okay. Okay. Number of photons may not be conserved because after all they are energy packets. If they deliver their energy to the particle with which they collide, probably they will disappear altogether. So number of photons, okay, may not be conserved. Okay, students, is that clear? I hope that is making sense, right? Then, as we have already discussed intensity of light in the previous videos of electromagnetic wave, but once again I would like to discuss these things because we'll be requiring this frequently in this discussion. Intensity and frequency of light. Now, student, by intensity we mean the energy, okay, crossing per unit time, per unit area. The plane of the area being perpendicular to the direction of propagation. For example, if light beam is going in this way, light beam is going this way. So, if you consider a unit area, the plane of the area being perpendicular to the direction of propagation and unit time interval, then the amount of energy crossing will be equal to the intensity. And as you know, since each photons carry a certain energy h nu, so the total energy crossing this area will be dependent on the number of photons. So intensity would directly mean the number of photons crossing per unit area, per unit time, plane of the area being perpendicular to the direction of incident rays. So it has everything to do with the number of photons. Remember, students, this, okay? It has everything to do with the number of photons. Then frequency decides the energy of each photon. Every single photon carries a certain energy, h into nu, where h is the Planck's constant. It's a universal constant, students, and nu is the frequency. Okay. So if we are changing the frequency, we are essentially changing the energy of every single photon coming out of the light source. And if we are changing the intensity of light source, then we mean we are changing the number of photons coming out from the light source per unit time and per unit area. Is it okay, students? So I hope that's making sense, right? So now the final explanation of this photoelectric effect was given by Einstein. So that is known as Einstein's explanation. Einstein's explanation. Okay, explanation. And also we'll see Einstein's equation. Einstein's equation. Okay. So it simply explained that when light is made incident on a photosensitive metal, so it interacts with the metal in the form of photons, that is discrete energy packets, photons. And these photons, when they strike the electron, okay, they impart their entire energy to the electrons, and with the help of that energy, they are able to overcome the attractive forces in the form of work function, and then if they carry any excess energy, that will be in the form of kinetic energy. Okay, so I'll write some. Suppose E is the energy of every single photon. That is energy acquired by the electron when the photon strikes the electron. Now this energy of the electron is utilized in two ways. A part of it will be spent to overcome the attractive forces so that it comes out of the surface. So it will require certain energy to overcome the surface bonds. You can call it as surface bonds. Okay. So that it comes onto the surface. And if anything is left over, then that will be in the form of kinetic energy. So this is basically the law of conservation of energy, you can say. How the energy of the photon acquired by the electron is utilized by the electron. So this is a kind of law of conservation of energy. This equation. Now in this equation, there will be certain photoelectrons which will be fortunate enough to spend the minimum energy required to come out. And what is that minimum energy? That is a work function. So if they are left, they spend the minimum energy, then naturally they will be left with maximum energy. So this equation is known as Einstein's photoelectric equation. This is the Einstein's photoelectric equation. Okay, student? Now suppose we replace this with the frequency, in terms of frequency of the incident photons. Then you can write like this. Now imagine we are decreasing the frequency of the incident light. Then what will happen? The energy of every single photon will reduce. So automatically the energy acquired by every single electron will reduce. A stage will come when the frequency has been reduced to such a value, say nu naught, that it is just equal to the work function of the substance. So in such case what will happen? There will be no kinetic energy. Even the maximum kinetic energy is zero. That means photoelectrons are just able to come out. So that frequency, that minimum frequency which is required in order to observe photoelectric effect is known as the threshold frequency or the cutoff frequency. We'll call it as the threshold. Threshold means limiting. Cutoff, also known as cutoff frequency. Threshold, this is D, sorry, students. Okay. So we can rewrite this equation as h nu is equal to h nu naught plus k max, assuming that frequency is greater than the threshold frequency. In terms of wavelength also, we can write nu can be replaced by c by lambda, and the wavelength corresponding to the threshold frequency will be known as threshold wavelength. So lambda naught will denote it with lambda naught to threshold frequency or cutoff frequency. Okay. So all this can be utilized here. Okay, students. Now one basic thing we have to understand before we wind up this video. The basic thing is this: not all photons are effective in ejecting photoelectrons, because the efficiency is very less, maybe 1 in 1 million or 1 billion. I'm just guessing, I don't know the exact thing. So billions and millions of photons might be able to eject one electron. But now what happens with the rest of the photons? They are simply, their energy gets dissipated, because it's not necessary that every single photon will straight away go and strike the electron. Okay, some photons might strike within the interatomic space, and if they don't straight away collide with the electrons, their energy will be absorbed and the atoms will keep vibrating. That's so the energy obtained from these photons which increase the thermal energy of the ions and electrons and all. Now if an electron is hit straight away by the photon, chances are there that it will come out. But again, I told you chances are there, because not every electron is fortunate enough to come out, because certain electrons have to spend the entire energy to come out. Maybe still they are not able to come out. I'm talking of electrons which are deep inside the metal surface. They may not be able to come out with the acquired energy. Then second of all, the electrons which have acquired the energy and which have been able to come out, will be coming out with a range of kinetic energies. The electrons which will be coming out in the photoelectric effect will be coming out with a range of energy, because some electrons will be fortunate enough to have maximum kinetic energy, whereas some less fortunate electrons will be just able to come out, just able to come out. That means they don't have any kinetic energy as well. So just they managed to come out, that's all. So that means there will be a range of kinetic energy for the photoelectrons coming out of the uh, photosensitive metal. Okay, students. So we'll stop here and we'll continue in the next video. Thank you so much for watching.